Any questions? All right. All right, so I have two objects that are heading towards each other, and they're going to collide. While they are touching each other, they're going to hit at this dotted line here. There's going to be some movement. And then they're going to separate. Let's say that they separate at this point. And all these boxes A should look the same size, all the ones B should look the same size, and so on. In this particular scenario, we're going to have them bounce off of each other. So they're heading towards each other, they're going to hit. There'll be some movement while they're touching, and then they will separate. So while they're interacting with each other, there are three things that are the same for both objects. Three quantities that are the same for both objects. What are they?
Do we know if the weight's the same?
Assume that it is not.
Normal force?
Narrow that down.
Either on the two boxes or, yeah, the normal force on the two boxes.
So close, so close. How do I know that the normal force that they exert on each other is not the same? What can you tell me about force? Something about force?
Can I try to reword it?
Okay.
Normal force between the two boxes?
Still so close, but
We know it's not the same because they don't stop. Like the forces don't cancel each other out
why do the forces not cancel each other out?
because they're not the same. Like they're not equal to each other.
Oh, no.
Or
No, I
the
think
boxes
you,
are moving after them.
I think Rachel's wording was a little bit better. All right, anything about forces? This is going to make the test next week interesting. I guess we had established there's something called a normal force.
they're pushing on each other. Is
Okay.
that what I was missing?
They're pushing on each other,
They're pushing on each other in perpendicular
okay,
with the normal force.
but how do I know the normal forces are not the same?
I could be wrong, but is it because it's like box B, it moves a bit more than A, like according to that drawing?
Did they move a different amount?
Like, the way I see it, it's like,
They first make contact. First make contact here. And then they stop. So this is the point which they hit, and this is the point at which they separate.
okay, never mind.
Chikara?
Do you know like how fast it's going since acceleration is proportional to force?
So you're saying, well, what's the last thing that you said just then?
That acceleration is proportional to force, correct?
Okay, so that's one thing we know about forces. The acceleration is proportional to the force.
And so like when it splits, it's the displacement because it's changing direction.
So you're saying the displacement's the same for both of them?
I mean, I would assume because they change direction at the same time.
Okay.
Change position.
So one of the things that they have in common is their displacement. So during the point of contact, B is basically going from there, is displacing that far. And, oh, no, sorry, that was badly done. There we go. So center to center, and A displaces that far. So they will both have the same displacement while they're touching each other.
Is there a constant force acting on both of them?
No, there would not be a constant.
So
You mean that, not the way that's worded, depends on what you mean by that.
Like, are they constantly being pushed, or is it just like the momentum from?
They're constantly being pushed.
So then why would they not like go in one direction? Like whichever one has the greater force. Move.
Oh, why would they move something like this?
Yeah. Or,
Well, this has to slow down. I mean, B slows down and eventually gets pushed backwards. A turns around much faster and gets pushed backwards. Having a force on you, if I'm moving this way and I get forced that way, it's gonna slow me down before I get pushed back. The point at which A turns around is not in the drawing. Or maybe it turns around instantly. But A has to slow down, stop, and then turn around.
so then what makes that forces like change? So if it's like constantly acting on the boxes, what makes it?
All right, if the two force, if, before they touch, how much force is acting on them? Before they're touching, what's the normal force?
Nothing.
Okay, after they separate, what is it?
Nothing.
Okay, so
Oh.
if the force starts at 0 and ends at 0, but we know there's something in between, it has to change. It doesn't stay 0 the entire time, so it starts at 0, and then the force increases, and then comes back to 0. That's what I mean, the force is not constant.
Okay.
They're still, while they're touching, they still exert a force on each other that entire time, but the force they exert is not constant.
Okay. That's what I was thinking. It was like the whole time.
Okay. Yeah, they are pushing a force the entire time, which is a clue there. Rachel, you said O?
I was gonna say, the part I was missing was while they were touching, there's a normal force on the boxes while they're touching.
Still missing it. What can you tell me about force? It's a rather important thing. We did the ropes outside, out in the hallway, to sort of illustrate it.
The direction matters.
So, keeping that in mind, how would you word that? What Rachel first said. Which way is the force that B exerts on A? Okay, which is the way that that A exerts a force on B?
Right.
Why can't the forces be the same?
There's a reason for sure.
Cause when they stop, right?
It's not a matter of stopping. I heard more than one person say it, but Stephanie,
They were going in different directions.
what's going in different directions? Yeah, the forces are in different directions, so they cannot be, the force cannot be equal. But Rachel was partly right. What is equal considering the forces? All right, let's draw it out a little bit. Is force a vector or a scalar? I heard,
Vector.
okay, which means,
It has a direction.
and,
Magnitude.
okay, so what is the same in terms of the forces?
Magnitude.
Yeah, the magnitude of the force, and that might be what you intended, but the magnitude of the force they exert on each other is the same. The direction is not. So we have that one of these is gonna work. The force that the force on A from B is equal to the force on B from A. That's just shorthand notation. The magnitude of the force, let's emphasize magnitude, put the vector symbol over it, the absolute value symbols. To indicate I'm just looking at the magnitude. Now the direction, I know are opposite each other. It's Newton's third law. A will push on B, B will push on A, but they'll push in opposite directions. So I can write the exact same thing, taking the idea of direction into it, and just the shorthand notation. Doesn't matter, one of them's negative. And this is just shorthand for saying the force on A from B is in the opposite direction but equal in magnitude to the force on B from A. All right, and we also had from Chikara that the displacement is the same. The displacement of A is equal to the displacement of B. And there's one more thing that is common to both of them. And it is so obvious that most groups don't think about it.
Is it the friction?
Let's assume that force is already taken care of. We have a limited number of quantities. I know force is the same in magnitude, but acceleration won't be because the masses, we assume, are not the same.
It'll be the velocity.
Velocity will not be the same. If they were the same, this dotted line would be smack dab in between them, but I tried to draw that dotted line closer to B.
Gotcha.
How many more quantities are there?
Position.
Oh, position won't be the same because they're not right on top of each other. Or overlapping.
Are we calling that initial force and other force? When they're coming in on each other?
I mean, before they touch?
Yeah, like would they have the same other force? Cause they're,
Not necessarily. We don't know how they started. They're just heading towards each other. As we tune in, coming back from the TV commercial, they're heading towards each other.
Tension would technically be the same because there's none. On both.
True. Forces taken care of. We don't have to do any more forces. but you're right. Well, here's possibly my most obscure clue. It's the name of a Bobby Sherman song. Your parents might know. Years ago, I had a student who actually had been to a Bobby Sherman concert back in the 70s. His older sister was a big fan. Is there a Pink Floyd song with the same name?
Is it energy or momentum?
The momentum of them will not be the same, but we will connect it with momentum and energy. Energy of them is not necessarily the same. And the next one, the last thing that's missing, the one that's so obvious, is a quantity that we've been dealing with since near the beginning. Really prominent in chapter 3. Sorry? Force is already taken care of, as you're thinking of that.
Mass.
Pardon?
Mass.
Another quantity that's not up there, but no, let's not assume that the masses are the same.
Acceleration due to gravity.
Well, we potentially the same, but there are some subtleties in there, which maybe not. I'm just trying, what other quantities are there? Something that can be measured. When I say quantity, something that can be measured.
It's not time, is it?
It is time,
But we don't have any numbers.
but they touch each other for the same amount of time. I told you it was so obvious, people miss it. They touch each other for the same amount of time. It's impossible for A to be touching B longer than B touches A. Now, I go through this exercise to bring up, these are things that we have studied already. If I look at combine these two ideas right here, I get into the idea of work and energy. If I combine this and this, the forces and the time, we get into the idea of momentum and impulse. Now I'm going to take you through a derivation. Not because I want you to memorize this derivation, but just again, just for you to see that this stuff comes from somewhere. So we're going to start out with the fact that they exert the same force, same magnitude of force on each other, just opposite directions. So questions before I get into the alphabet soup. All right, so I'm starting out with the force on A from B is equal to the force on B from A. All right. They exert force on each other for the same amount of time, so I'm just going to multiply both sides by the time. Time equals the force. From Newton's second law, what is force equal?
Acceleration time.
I heard mass times acceleration there.
I was gonna say acceleration time fast, so.
Okay. Just making sure you weren't stopping at just acceleration.
No.
All right. So that's negative. That is the mass of, this is the force on A. So it's the mass of A times the acceleration of A times time is equal to the mass of B times the acceleration of B times time. These are vectors here. It's supposed to be a vector symbol. All right, so what is acceleration times time? Acceleration times time. It's a chapter 3 thing. Close?
Change in velocity.
Yes. That's equal to the change in velocity, so if negative, whatever the mass of A is, times the change in velocity of A is equal to the mass of B times the change in velocity of B. And change is just final minus initial. So negative mass, apparently that didn't work, there we go. Mass of A times, that's the final velocity of A minus the initial velocity of A equal mass of B times the final velocity of B minus the initial velocity of B. So I got one more really long step and then we're gonna shorten it. All right, so I've got a number out here. This would represent some number of kilograms. And then I've got two things inside separated by a minus sign. We're gonna distribute. So just as a flashing back, if I had 3x minus 4, that's, I multiply 3 times x, minus 3 times 4, so distributing. So I'm gonna distribute, this is the longest of the steps.